This is my trigonometry course. Today we're going to use the Pythagorean Theorem to help us find the values of trigonometric functions. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. We're going to review the Pythagorean Theorem. For most of you, this is something that you know pretty well by now. But in my curriculum, we may not have seen this for a while. If you have a right triangle and, well, as we've mentioned, these side lengths, they're A and B, and we call those sides the legs of the right triangle, and this side we call the hypotenuse. The Pythagorean theorem tells us that the sum of the squares of the side lengths of the legs of the triangle is equal to the square of the length of the hypotenuse. So let's do some practice problems. Again, this is probably going to be a review for a lot of students, but we're just going to get through these quickly. So the theorem tells us that a squared plus b squared is equal to c squared, and we're going to use that to find the missing side here. Now, the most important thing to understand is that the hypotenuse is always going to be c. Don't plug in one of the legs into c, or else you're going to get the wrong answer. So we have 15 squared plus 8 squared is equal to x squared. And if we add those up, we get 289. And we need to square root both sides, and whenever you square root both sides of an equation, you have to write a plus or minus symbol. That's one of the most common mistakes that students make in the math curriculum. So x is plus or minus 17. And remember that a side length cannot be negative. In the subject of trigonometry, side lengths are negative when you're moving triangles into the four quadrants, but we're assuming that this triangle is a real-world triangle, so there is no such thing as a negative side length. So the hypotenuse is always the opposite side of the right angle, and so that number goes here. That number is c. So let's try another example. Again, we're going to use the Pythagorean theorem. And this theorem only works for right triangles, by the way. I should have mentioned that. So in the previous problem, we were looking for the hypotenuse, but in this case, we have the hypotenuse. That goes there. That's c. So we have y squared plus 9 is equal to 15. Squaring is the opposite of square rooting, so they're opposite operations. So if we square the square root 15, the root just disappears. And now we're going to square root both sides of the equation. Remember, whenever you square root both sides of an equation, you need to write a plus or minus symbol. But we're assuming that these triangles are real-world triangles, so you cannot have a negative side length. Now, that's not exactly true when you are doing trigonometry problems, but in the real world, you cannot have a negative side length. So let's do one more of these problems before you try one on your own. Seven is the hypotenuse, the side opposite the right angle. Subtract 25 from both sides, and we get 24. Then we're going to square root both sides. Whenever you square root both sides of an equation, you have to write a plus or minus symbol. And 24 is 4 times 6. And we've learned in previous courses, the square root of AB is equal to the square root of A times the square root of B. So A is equal to plus or minus square root 4 times square root 6. And the square root of 4 is 2. And we can get rid of the dot. You don't have to show every single one of these steps. But again, we're reviewing the basic concepts. So I'm showing more steps than necessary. And of course, if we're assuming this is a real-world triangle, then your answer has to be positive. There's no such thing as a negative side length. Okay. So now it's your turn. Go ahead and try example 4. And when you come back, we'll do it together. All right, we're back. So X is one of the legs of the right triangle. 10 is the hypotenuse. And you don't really have to show this square root step. You can skip from here to here where we show that X is equal to plus or minus 8. That's fine. But of course, we're not allowed to have a negative side length unless we are moving triangles around the quadrants, which we are going to do later on in this class. So if you got 8, good job. Okay, try example 5, and when you come back, we'll do it together. All right, we're back. So in this problem, we're looking for the hypotenuse. That's y, the side opposite the right angle. Nine plus 5 is 14. And if we square root both sides, we get plus or minus root 14. I'm not going to show the square rooting both sides. And again, if we assume that this is a real-world triangle, then our answer is going to be positive root 14. So if you got that answer, good. Go ahead and try example 6, and when you come back, we'll do it together. All right, we're back. So again, this is a right triangle, so we can use the Pythagorean Theorem. The hypotenuse is 9. And 81 minus 36 is 45. If we square root both sides, then we have a perfect square. We can factor to 9 times 5. And we can separate to a product of 2 roots. And that is this principle, the square root of a times b is equal to the square root of a times the square root of b. So the square root of 9 is 3, and we can get rid of the dot. And we assume that the side is positive. So if you got that answer, excellent. We went through that pretty quickly because for most students, they're going to know that pretty well at this point. But I think it's been a while since we went over that in my geometry curriculum. Okay, so in these problems, we're given the value of one of the trigonometric functions, one of the 6 functions. In this case, we're given the sine ratio, and we're asked to find all of the other ratios. So we have some angle theta, and we're given the sine of that angle, the sine value, and we're asked to find all these other values of that angle. So we're told that theta terminates in quadrant 2. So what that means is our angle stops there, and we can draw a generic triangle. Your triangle doesn't have to be the exact shape. We just need some generic triangle. And of course, this green angle is the reference angle. And we're told that the ratio of the opposite side of the reference angle and the hypotenuse is 1 over root 5. But that doesn't mean that the actual length of the opposite side is 1 and the length of the hypotenuse is root 5. We actually don't know the lengths. All we know is the ratio of the side lengths. So there may be an unknown factor. Remember, when you divide numbers, sometimes your fraction can reduce, so we don't know exactly what the side lengths are. Now, sine is the opposite side over the hypotenuse, so we'll write x over here and x root 5 here. And in order to find the other values, the 5 remaining values, we need to calculate this length here, or we need to find some number that gives us a relation between the sides. But x is going to cancel out for every one of our ratios. So we don't really care exactly what x is. X can be 1 billion, it can be 1 million, it can be 2, it can be 3/2. It doesn't matter what x is. In our ratios, x is always going to cancel out. So what that means is we can choose any value for x. And we're going to choose a very convenient value. We're going to let x equal 1. Because again, the triangle can be any size, as long as it has the general shape that we want. It doesn't make a difference how big or small it is, because again, we're looking for ratios. And the reason that we're letting x equal 1 is because we don't want to have to deal with x when we use the Pythagorean theorem. So that's what we're going to do to find this missing side length. We're going to use the Pythagorean theorem. So if we let x equal 1, then we can write our triangle now. This side is 1, this side is root 5, and this side we don't know. So now we're dealing with this triangle with x equal to 1. And we're going to use the Pythagorean theorem to find the missing side. Again, we don't actually know the side lengths. This information up here doesn't actually tell us the side lengths. But again, it doesn't matter what the exact lengths are. We just want the relation between the lengths. So now we're going to use the Pythagorean theorem. And we have 1 squared plus b squared is equal to the square root of 5 squared. So we have 1 plus b squared is equal to 5. Subtract 1 from both sides. And if we square root both sides, we get b is equal to plus or minus 2. And you don't have to show the square rooting. That's okay. You don't have to show that. You can if you want to, but we need to know, is b negative or positive? Think about that. Is b negative or positive? Well, the triangle tells us this length is to the left of the y-axis, so that means it must be negative. So now we can draw a triangle. And I'm going to choose a different color. And this side is going to be -2. This side is going to be 1, and this side is √5. And the actual angle that we're talking about, theta, is whatever this angle is here. And the reference angle, of course, is this green angle. Now, you don't have to show the angle, you don't have to have these colors, you don't have to do a lot of this. You just want to know these sides, their relation to each other, so we can find cosecant theta. So now we're going to use this triangle to help us figure out the values of these remaining functions. So cosecant theta is defined as the hypotenuse divided by the side opposite the green reference angle. So there you go. I'm using this triangle here. Secant theta is defined to be the hypotenuse divided by the side adjacent the green reference angle. And cotangent theta is defined to be the side adjacent the green reference angle over the opposite side. Cosine theta is equal to the adjacent side of the green reference angle divided by the hypotenuse. I'm going to multiply both sides by √5. To rationalize the denominator, and tangent theta is defined to be the opposite side of the green reference angle divided by the adjacent side of the green reference angle. So there you go. So once you have this triangle, you can find your values very, very quickly. And when you get used to these problems, you're going to do these very, very quickly, much quicker than we just did them together. But we're explaining every single step. So that's the general procedure. All right, so let's try another one of these problems. So we know that alpha terminates in the fourth quadrant. So we can go ahead and draw our angle. And we don't know the exact angle. We just know that it terminates in the fourth quadrant. So we're just going to draw a generic triangle. Doesn't have to be the exact side lengths that we need, just some generic triangle. And this red angle is alpha. And the reference angle, of course, is the green angle. And we know that tangent alpha is equal to -5/12, but we don't know the actual side lengths of whatever triangle this is referring to. So we'll say 5x over 12x, because some factor may cancel out when we divide. We don't know the lengths are 5 and 12. We just know that the ratio of the lengths is 5/12, -5/12. Now, because the angle terminates in the fourth quadrant, we know that this side is negative. So this side is -5x, and this side is +12x. So we know that the 5x is actually the negative side. So we need to find the missing side so that we can use it to calculate the other trigonometric ratios. So we're going to let x equal 1. That's convenient. So this side is 12 if x is 1. And this side is -5. And we'll call this side C. And we're going to use the Pythagorean Theorem. So 12 squared plus -5 squared is equal to c squared. So we have 144 plus 25 is equal to c squared. 169 is equal to c squared. We're going to square root both sides. Remember, you always have to write a plus or minus symbol when you square root both sides. even though we know that the hypotenuse must be positive. Remember, the hypotenuse is always defined to be positive, so we can change our final answer in that equation to positive 13. So now we know that the hypotenuse is 13, so we can draw our final triangle. And you don't need to show this step here. You can skip that if you want. So this side is -5, this side is 12, this side is 13. We have our green reference angle, and the actual angle in question is this red angle here, which is alpha. So now we're ready to find our ratios. So cosine alpha is the adjacent side of the green reference angle divided by the hypotenuse. Sine alpha is the opposite side of the green reference angle divided by the hypotenuse. Cosecant alpha is the hypotenuse divided by the opposite side of the green reference angle. Secant alpha is the hypotenuse divided by the adjacent side of the green reference angle. And cotangent alpha is the adjacent side of the green reference angle divided by the opposite side of the green reference angle. So there you go. Let's try one more problem before you attempt one on your own. So in this problem, we're told that omega, the angle, terminates in quadrant 3. So we'll draw the angle, and we don't know exactly what the angle is. So we're just drawing some generic angle in quadrant 3. And the angle is omega, and of course this green angle is the reference angle. We don't know the actual side lengths of the triangle. We just know that the ratio of the hypotenuse and the adjacent side of the green reference angle is -√7/2. Now we know that the negative symbol must be on the 2x, because the hypotenuse is never negative. So the hypotenuse is x√7, and the adjacent side of the green reference angle is -2x, which makes sense because this side has to be negative. It's to the left of the y-axis. So to make things convenient, we're going to let x equal 1. And that means that this side is -2, this side is √7. And we need to find that missing side so that we can find the cosine, sine, cosecant, tangent, and cotangent ratios. So we're going to use the Pythagorean Theorem. So -2 squared plus b squared is equal to c squared. So we have 4 plus b squared is equal to 7. And b squared is equal to 3, square root both sides, and we get plus or minus √3. Now the big question is our answer positive √3 or negative √3? Look at this triangle and ask yourself, is this side going to be negative or positive? Now the hypotenuse is always positive. So in the previous problem, we knew that our answer is going to be positive down here because the hypotenuse is always positive. But now we're talking about a leg, so obviously you can see this side is below the x-axis, so b is actually going to be negative √3. So now we can draw our final triangle that we're going to use. And this side is negative √3. The hypotenuse is root 7, and this side is negative 2. So the angle in question is this angle here. And of course, we need to consider the green reference angle. And the red angle is omega. So you don't have to draw quite so many things on the page. We're just doing this so you can see what's going on. So cosine omega is the adjacent side to the green reference angle divided by the hypotenuse. Multiply both sides by root 2 or root 7, and we rationalize the denominator. Sine omega is the opposite side of the green reference angle divided by the hypotenuse. Multiply both sides by root 7, and we get root 21 over 7, and we cannot reduce that. You cannot divide 21 by 7 because that's not 21. That's root 21. Cosecant is the hypotenuse divided by the opposite side. Multiply both sides by root 3, and we get root 21 over 3, negative root 21 over 3. Tangent omega is the opposite side divided by the adjacent side, which is root 3 over 2. And cotangent omega is the adjacent side to the green reference angle divided by the opposite side, the green reference angle, and the negatives cancel out. Multiply both sides by root 3, and there you go. So I want you to take a picture of these problems, and you're going to use them to do number 4. Be aware that theta terminates in quadrant 1, so your reference angle is going to be the actual angle. So you're going to rotate, and it doesn't matter exactly what the measure is, create a generic right triangle, and remember, we don't know what the side lengths are, but we know that cosine theta, the adjacent side of the reference angle, in this case the red angle, divided by the hypotenuse is equal to 3 over root 10. So 3x over x root 10. We're going to let these be the actual sides. So cosine is adjacent, the adjacent side, so that's going to be 3x over the hypotenuse, x root 10. So you're going to let x equal 1 to make things convenient and use the Pythagorean Theorem to find this missing side. So go ahead and try number 4, and when you come back we'll do it together. Okay, we're back. So again, we're going to let x equal 1 to make things convenient. We're going to draw the triangle, and the side lengths, again, they don't have to be exact. The only purpose for the triangle is just to give us an idea of what the side lengths are, and we're missing this side, so we're going to use the Pythagorean Theorem. Root 10, or 3 squared plus b squared is equal to root 10 squared. And if we solve, b is equal to plus or minus 1. And the question is b going to be positive 1 or negative 1? This side is above the x-axis, so it's going to be positive 1. And by the way, let's call that angle theta. So again, the reference angle in this case is the actual angle. So let's draw our final triangle. And again, you don't have to draw every one of these triangles if you don't want to. So this side is 3, this side is 1, this side is root 10. This angle is omega. And of course it's a right triangle. And we're ready to find the ratios. Sine theta is equal to the opposite side of the red reference angle divided by the hypotenuse. Multiply both sides by root 10. And we rationalize the denominator. Tangent theta is the opposite side of the red reference angle divided by the adjacent side. Cosecant theta is the hypotenuse divided by the opposite side, and so on and so forth. Secant is the hypotenuse divided by the adjacent side, and cotangent is the adjacent side divided by the opposite side. So there you go. If you got that one right, excellent. Okay, go ahead and try number 5, and when you come back, we'll do it together. Okay, we're back. So beta terminates in quadrant 3. And we're told that the ratio of the adjacent side to the opposite side is 4/3. The green angle is the reference angle, and we're in the third quadrant, so we know both of the legs must be negative. So this side is negative 4x and this side is negative 3x. That's very useful information. This angle, of course, is beta. And to make things convenient, we're going to let x equal 1. And we need to find the missing side. So we're going to use the Pythagorean Theorem. And we see that c must be equal to plus or minus 5, but remember the hypotenuse is always positive. So we found the missing side. So let's draw one final triangle to help us. Again, you don't have to draw so many triangles. And again, this angle is beta. And we need to consider the green reference angle as always. Without the green reference angle, then our functions wouldn't really have any meaning. Cosine beta is equal to the side adjacent the green reference angle divided by the hypotenuse. Sine is the opposite side the green reference angle divided by the hypotenuse. Cosecant beta is the hypotenuse divided by the side opposite the green reference angle. Secant beta is the hypotenuse divided by the side adjacent the green reference angle, and tangent beta is the side opposite the green reference angle divided by the side adjacent. So that reduces to positive 3/4. So if you got that one right, perfect. Good job. Okay. So why don't you try one more of these before we go on to a different type of problem. Go ahead and attempt number 6, and when you come back, we'll do it together. Alright, we're back. So this angle, omega, terminates in quadrant 4. And remember, you always have to start on the positive part of the x-axis. when you consider the angle. So the reference angle, again, is our green angle. And this angle is omega. So we know that cosecant omega is equal to x root 7 over -1, or negative x, that is. We don't know the actual side length, so that's why we're writing x's. We do know that the negative has to be on the x, because that represents the opposite side, which we can clearly see is negative in quadrant 4. And the hypotenuse is x root 7. We need to find the missing side, so we're going to let x equal 1. It's convenient to let x equal 1. Let's draw a hypothetical triangle. Again, a triangle doesn't have to be exact. So we're missing this side. We're letting x equal 1. So using the Pythagorean Theorem, -1 squared plus b squared is equal to square root 7 squared. So we have 1 plus b squared is equal to 7. And b is equal to plus or minus root 6. So is it positive root 6 or negative root 6? What sign is this side length? Well, this length here is to the right of the y-axis, so it must be positive root 6. So now we're ready to draw our final triangle that we're going to use to help us find the values we're looking for. And this side is positive root 6, this side is -1, and this side is root 7. The angle in question is this angle here, which is omega. And of course we need to consider the green reference angle. That determines a lot. Cosine omega is a side adjacent to the green reference angle divided by the hypotenuse. Multiply both sides by root 7. Sine omega is a side opposite the green reference angle divided by the hypotenuse. Multiply both sides by root 7 and we get root 7 over 7. Secant omega is the hypotenuse divided by the side adjacent to the green reference angle. Multiply both sides by root 6 and we get the following. And you cannot simplify these fractions because we can't divide root 42 by 7 or by 6. It's not 42, it's root 42. Tangent omega is the side opposite the green reference angle divided by the side adjacent the green reference angle. Multiply both sides by root 6 and we can rationalize the denominator. Cotangent omega is the side adjacent the green reference angle divided by the side opposite the green reference angle, so we get negative root 6. So if you got that one right, very good. Good job. Okay, so now we're going to do a problem that is very similar to the problems that we just did. This point lies on the terminal side of an angle in standard position. And we're asked to find the 6 trigonometric ratios of that angle. So let's plot this point. The point would be somewhere around here. It doesn't really have to be exact. Notice that I'm not using a grid. We don't have to be that precise. We just want to know that it's in quadrant 2, obviously. We're going to count out 2 and up root 5. So that point is on the terminal side of an angle in standard position. So we have some angle and the terminal side goes through that purple point there. So if this is the terminal side, it goes right through that point. So what we can do is we can draw a triangle, and again, it doesn't matter how big or small the triangle is. The shape of the triangle is determined by the angle here, and the fact that this is a right angle. So we don't really care what the lengths of the triangles are. We just want to know the ratios. This point can actually be anywhere on the terminal side of the angle. It can be up here, it can be up here, it can be down here. You're going to get the same answer because the shape of the triangle is going to be the same as long as the point is on the terminal side of that angle, as long as it's on this line. And the reason for that is this angle, this green reference angle, doesn't change if the point is on the terminal side of the reference angle, and obviously this angle here is always going to be a right angle. So the shape of the triangle doesn't change. So we can really choose any point, and the ratios are going to be the same. Sine is going to be equal to sine, cosine is going to be equal to cosine. But since we have these numbers, we might as well use those numbers. So we're going to make this side -2 and this side √5 just to make things convenient, because again, it doesn't matter what triangle you use as long as it's a triangle based on a point lying on the terminal side of the angle. And the angle, we can call it anything. It doesn't really tell us what the angle is. We'll just call it theta. So now we need to find the hypotenuse. So we're going to draw a triangle, and this side is -2, this side is √5. We need to find the hypotenuse so that we can find all the trigonometric values. And if we solve, we get c is equal to ±3, and the question is it going to be +3 or -3? And the answer is it has to be positive, because the hypotenuse is always a positive number. It's very important to remember that. So now we have what we need. Let's go ahead and draw a final triangle. This side is -2, this side is √5, and this side is 3. So the angle in question is this angle here, theta. And of course we need to consider the reference angle. And now we're ready to go. So sine theta is the side opposite the green reference angle divided by the hypotenuse. Cosine is the side adjacent the green reference angle divided by the hypotenuse. Tangent theta is the side opposite the green reference angle divided by the adjacent side. Cosecant is the hypotenuse divided by the opposite side of the green reference angle. And we have to rationalize the denominator by multiplying both sides by √3, or √5 that is. Secant is the hypotenuse divided by the side adjacent the green reference angle, and cotangent theta is the side adjacent the green reference angle divided by the side opposite. Multiply both sides by √5, and there you go. So as you can see, these problems are very similar to the problems that we did previously. So let's try another one. Okay, let's pick up the pace a little bit here. These problems are not going to take you that long to do. Here we're told that we have this point on the terminal side of an angle in standard position. So 3 and -1 might be, say, here. So that point is on the terminal side of an angle in standard position. So it goes all the way and it stops there. And we can just consider that to be the vertex, or a vertex of the triangle. My triangle's a little small there, but it'll still work. So we're making the green angle the reference angle. And what this means is that this side is 3 and this side is -1, and we have to find the missing side length. So if we draw a triangle over here, we're looking for C. So 3 squared plus -1 squared is equal to C squared. We're using the Pythagorean Theorem. And we're going to square root both sides, so we get plus or minus square root 10. And the hypotenuse, of course, is positive. It's always positive. So now we have the information that we need. And by the way, I should show that this point down here is 3, -1. That's that point there. All right. So we're ready to draw the triangle that we need to find these values. So this side is -1, this side is 3, and this side is root 10. And the angle theta is that angle there, and of course we need the reference angle. The reference angle determines pretty much everything. Sine theta is equal to the opposite side divided by the hypotenuse. Multiply both sides by root 10 to rationalize the denominator. Cosine theta is the side adjacent to the green reference angle divided by the hypotenuse. Multiply both sides by root 10 to rationalize the denominator again. Tangent theta is defined to be the opposite side of the green reference angle divided by the hypotenuse. Or excuse me, the adjacent divided by the adjacent side. Cosecant theta is the hypotenuse divided by the side opposite the green reference angle. Secant theta is the hypotenuse divided by the side adjacent the green reference angle. And cotangent is the side adjacent the green reference angle divided by the opposite side of the green reference angle. And so there you go. So given a point on the terminal side of an angle in standard position, we're able to find the 6 basic trigonometric functions of that angle. Okay, let's try a couple more of these problems. Here we have a point in the first quadrant that looks like it's maybe about there. So we'll make that point root 5, root 2. And this angle is in the first quadrant, obviously, so the reference angle is the actual angle. And this side is root 5, and this side is root 2. So all we need to do really is just use the Pythagorean Theorem to find that missing side. You can see these problems are really not that difficult. They just look very difficult. So root 5 squared plus root 2 squared is equal to c squared. So we have 5 plus 2 is equal to c squared. Square root both sides, and we get plus or minus root 7, but of course the hypotenuse always has to be positive. So now we're ready to draw a triangle. This side is root 2, this side is root 5, and this side is root 7. And the reference angle, again, is the actual angle. And so we're ready to go. And all the side lengths are positive. So sine theta is equal to the opposite side of the red reference angle divided by the hypotenuse. Multiply both sides by root 7, and we get the following. Cosine theta is the adjacent side divided by the hypotenuse. Multiply both sides by root 7, and we get root 35 over 7. Tangent is the side opposite the red reference angle divided by the side adjacent. Multiply both sides by root 5, and we get root 10 over 5. Cosecant theta is the hypotenuse divided by the side opposite. Multiply both sides by root 2, and we get root 14 over 2. Secant is the hypotenuse divided by the side adjacent. Multiply both sides by root 5, and we get root 35 over 5. Cotangent is the side adjacent the red reference angle divided by the side opposite. Multiply both sides by root 2, and we get root 10 over 2. So there you go. So we're doing a lot of things at once. There's too many things to even consider. So many different things. The Pythagorean Theorem, angles in standard position, coordinates, reference angle, reference triangles, the 6 basic functions. So many different things we're considering at once. So let's do one more of these problems, and then you can try some on your own. We haven't done a problem where theta has terminated in the fourth quadrant yet. Actually in the third quadrant. This one's going to terminate in the third quadrant, so we're going to go out 1 and down 7. So maybe it'd be about here. Again, this doesn't have to be exact. So we're going to make that point -1, -7. And the corresponding angle would be this angle here. And of course the reference angle is that green angle. And we're going to let this side be -1, and this side is going to be -7. Okay, so now we're going to draw our triangle up here just to demonstrate what we're looking for. We're looking for C. We're going to use the Pythagorean Theorem. So we have 49 plus 1 is equal to C squared. Then we're going to square root both sides. And of course, whenever you square root both sides of an equation, you need to write a plus or minus symbol. But remember, the hypotenuse is always positive. So 50 is 25 times 2. We're going to use that principle that we learned in previous classes and previous courses. We're going to pull out that perfect square, and we can get rid of the dot. We don't really need the dot. When you put a number right next to a root, that means you're multiplying the number, the yellow number, by the green root. So the hypotenuse is 5 root 2. So now we're ready to draw a triangle that we're going to use to find all the values we're looking for. And this side is 5 root 2, this side is -7, and this side is -1. So the angle in question is this angle here, and of course we're going to use the reference angle to help us. So sine theta is equal to the side opposite the green reference angle divided by the hypotenuse. Multiply both sides by root 2, and we get negative 7 root 2 over 5 times 2. So when you multiply root 2 by root 2, you get 2. Then we're going to multiply those together, and we get negative 7 root 2 over 10. And let me make this more orderly. So that is sine theta. And you really want to avoid making your negative symbol disappear on that fraction. So I have to write that better. We don't want to get into bad habits. Cosine theta is equal to the side adjacent the reference angle, the green reference angle, divided by the hypotenuse. Multiply both sides by root 2. And again, we get 5 times 2. So negative root 2 over 10. That's cosine theta. Tangent theta is the side opposite. So negative 7 over the side adjacent. And cosecant theta is a side, it's the hypotenuse divided by the side opposite. And secant theta is the hypotenuse divided by the side that's adjacent to the green reference angle. So we get negative 5 root 2. And cotangent theta is the side adjacent the green reference angle divided by the side opposite the green reference angle, so we have positive 1/7. Okay, so at this point, you're ready to do some of these problems on your own. So go ahead and attempt number 11, and when you come back, we'll do it together. Okay, we're back. So we need the point 5, negative 11. So that's going to be maybe about there. It doesn't have to be exact. Five negative root 11. Did I say 11? I meant root 11. So this side we can say is 5, and this side we can say is root negative 11. And the angle in question obviously is this angle here, that's theta. And we need to use the green reference angle. So to speed things up here a little bit, I'm going to just use the Pythagorean theorem. I'm not going to continue to draw triangles. We're looking for the hypotenuse, so we have 25 plus 11 is equal to c squared. 25 plus 11 is 36. Square root both sides, and we get plus or minus 6, but of course the hypotenuse always has to be positive. So I guess I'll draw one triangle down here just so we can see what's going on. So the triangle would look something like that. Again, all that matters is that it's a right triangle. It doesn't matter if it's the exact side lengths, because we're just using the triangle to help us find the answers. So this is the angle in question, theta. And of course we have the reference angle. So sine theta is the side opposite the green reference angle divided by the hypotenuse. Cosine theta is the side adjacent the green reference angle divided by the hypotenuse. Tangent theta is the side opposite the green reference angle divided by the side adjacent the green reference angle. Cosecant theta is the side it's the hypotenuse divided by the side opposite the green reference angle But of course we have to rationalize the denominator, so we're going to multiply both sides of the fraction by root 11. Cosecant theta is the hypotenuse divided by the side adjacent the green reference angle. And cotangent theta is the side adjacent the green reference angle divided by the side opposite the green reference angle. Multiply both sides by root 11, and there you go. All right. So you can take a picture of these two problems if you'd like to help you with number 12. I want you to do a number of these problems so you can get used to what we're doing here. So go ahead and try number 12, and when you come back, we'll do it together. Okay, we're back. So now we are in the first quadrant. This point is in the first quadrant. Again, that point is on the terminal side of a reference angle, or an angle in standard position. So we can assume this side is 3, this side is 2, and we're going to use the Pythagorean Theorem to find the hypotenuse. And when we do that, we have c is equal to root 13. So now we can draw our final triangle that we're going to use down here next to our values that we're looking for. So this side is 2, this side is 3, this side is root 13. And the reference angle is equal to the actual angle. That's theta. So now we can use that triangle to help us find these values. Sine theta is the opposite side divided by the hypotenuse. Cosine theta is the adjacent side divided by the hypotenuse. Tangent theta is the opposite side of the red reference angle divided by the adjacent side of the red reference angle. Cosecant theta is the hypotenuse divided by the opposite side of the red reference angle. Secant is the hypotenuse divided by the adjacent side of the red reference angle. Cotangent is the adjacent side of the red reference angle divided by the opposite side of the red reference angle. So there you go. So if you got that one right, excellent. Okay, go ahead and try number 13. Remember, this point is on the terminal side of an angle in standard position, and you want to find all of the 6 basic trigonometric functions of that angle. So when you come back, we'll do it together. Okay, we're back. So we're going to go to the left root 6 and down root 7. So that would be maybe about there. It doesn't have to be exact. So that point is negative root 6, negative root 7. And this is the angle in question, the angle that we're talking about. And of course we have to consider the green reference angle. This side is negative root 6 and this side is negative root 7. And we have to find the hypotenuse. So we're going to use the Pythagorean Theorem. So we get 6 plus 7 is equal to c squared, and we get 13. We got the same number that we did in the previous problem. And remember, 13 has to be positive because we're talking about the hypotenuse. Hypotenuse is always defined to be positive. Okay, so the hypotenuse is root 13. This side is negative root 6. This side is negative root 7. The angle in question is this angle here, Maybe I'll move that root 6 over a little bit so we can see. It's this angle here. Of course, we have to consider the reference angle. So sine theta is the opposite side of the green reference angle divided by the hypotenuse. Multiply both sides by root 13 and we get negative root 91 over 13. Cosine theta is the adjacent side of the green reference angle divided by the hypotenuse. Multiply both sides by root 13 and we get negative root 78 over 13. Tangent theta is the side opposite the green reference angle divided by the side adjacent the green reference angle. The negatives cancel out, multiply both sides by root 6 and we get root 42 over 6. Cosecant theta is defined to be the hypotenuse divided by the side opposite the green reference angle. Multiply both sides by root 7 and we get negative root 91 over 7. Secant theta is defined to be the hypotenuse divided by the side adjacent the green reference angle. Multiply both sides by root 6 and we get negative root 78 over 6. And sorry, we're kind of running out of room here. Let me make some more room. So cotangent is the side adjacent the green reference angle divided by the side opposite the green reference angle. The negatives cancel out, multiply both sides by root 7 and we get root 42 over 7, and no, that cannot be reduced. 42 divided by 7 is 6, that is correct, but that's not 42, that's root 42. Alright, if you got that one right, good job. Try one more of these problems before we have a final problem set. Go ahead and attempt number 14, and when you come back, we'll do it together. Alright, we're back. So now we're going into quadrant 2. So we're going to move out root 2 and up 5. So that gets us to about there. Again, the triangle doesn't have to be perfect. You don't need to use grid paper. This triangle is just going to help us find or picture what's going on. So that point is negative root 2, 5, which means that this length down here is negative root 2 and this length is 5. The angle in question is this red angle here, and the reference angle, of course, is this green angle. So we're going to use the Pythagorean Theorem to help us. Find the hypotenuse. So we have 25 plus 2 is equal to c squared. C squared is equal to 27. C is equal to the square root of 27, and we know that I should probably write plus or minus just so I can reinforce that idea. Whenever you square root both sides of an equation, you always write a plus or minus symbol. You can get rid of it later on, but you need to get in that habit. So c is equal to the square root of 9 times the square root of 3. I don't think I did that in the previous problem, but I really should. So c is equal to plus or minus square root 13, but of course it's the hypotenuse, so it's positive square root 13. Okay, so square root of 9 is 3, so we have 3 square root 3. Again, when you put a number right next to a root, that means you're multiplying the yellow and the green numbers. Students have a lot of trouble with that, but that's why we covered that in my intermediate algebra course and my beginning algebra course. And I think we even covered that in my geometry course a little bit. So now we can draw a triangle. This side is negative root 2, this side is 5. And we found that the hypotenuse is 3 root 3. The angle in question is this angle here, theta. And of course the reference angle is very important. So now we are ready to find our values. Sine theta is the opposite side of the green reference angle divided by the hypotenuse. We're going to multiply both sides of the fraction by root 3. And what that does is it changes that root 3 to a 3. And then when we multiply the denominator, we get 9. Cosine theta is equal to the adjacent side of the green angle divided by the hypotenuse. Multiply both sides of the fraction by root 3 and we get root 6 over 3 times 3, which again simplifies to root 6 over 9. Sorry that it's kind of cramped here. Tangent theta is the side opposite the green reference angle divided by the side adjacent. Multiply both sides by root 2 and we get 5 root 2 over 2. Cosecant theta is the hypotenuse divided by the side opposite the green reference angle. Secant theta is the side, well, it's the hypotenuse divided by the side adjacent the green reference angle. Multiply both sides by root 2 and I get 3 root 6 over 2, negative 2. And cotangent is the side adjacent the green reference angle divided by the side opposite the green reference angle. So let me provide a little more room here. And technically we probably want to put our negative right next to the fraction, but you see I have kind of limited room, so I'm kind of writing sloppy. Okay, so if you got those answers, perfect. So the only thing that changes when you go from quadrant to quadrant, assuming that your reference angle is the same, when you go from quadrant to quadrant, the signs of the trigonometric functions change. So now we're going to do some problems where we don't really have to use the Pythagorean theorem, because the next problems are going to correspond to these 30, 60, 90 triangles and 45, 45, 90 triangles. So get a picture here. You should know these triangles pretty well by now, but get a picture of that. So we have a point 4, negative 4 root 3, which might be, say, here. That's a point on the terminal side of the unangled and standard position. And so this point here is 4, negative 4 root 3. So that means that this side is 4, this side is negative 4 root 3. So what that means is the angle in question is this angle here, and the reference angle is this green angle, of course. But we don't really have to use the Pythagorean theorem, because we can see that this is a 30, 60, 90 triangle. If this side is x and this side is x root 3, then that means that this side is 2x. We recognize these sides, or the relation between the two sides. So in this case, x, and by the way, this should be negative for this particular problem, we can see that x is 4. So what is the hypotenuse? Well, the hypotenuse must be 8. So let's draw that triangle again. So this side is 4, this side is negative 4 root 3, and the hypotenuse is 8. And let's draw that red angle so we understand what's going on here. And of course, the, whoops, I need to draw it like so. The green angle is here. And we actually know what the green angle is. Can you guess what the green angle is? If this side is 4 root 3 and this side is 4, then we know that the green angle is either a 30-degree angle or a 60-degree angle. So look at these angles inside here. I'm going to create another color here. This angle must be 30 degrees, it's opposite x, and this angle must be 60 degrees. So we can figure out what that angle is pretty much immediately. The green angle is 60 degrees. So we could just plug in whatever that red angle would be. We can calculate that red angle. It's just 360 minus 60. So theta is equal to 300 degrees. We can calculate that. And the green angle is 60 degrees. But we don't really need the measure of the angle because we have our triangle right here. You could use it if you wanted to, but we have our triangle there, so let's go ahead and calculate the values. Sine theta is the opposite side of the green reference angle divided by the hypotenuse. And we have to reduce this fraction. 4 over 8 reduces to 1 over 2. And doesn't that look familiar? Negative root 3 over 2. That looks very familiar. You see, if you have the triangle in your head, the 30, 60, 90 triangle in your head, you can just consider these sides to be x and 2x. But in this case, we actually have the side lengths. Cosine is the adjacent side of the green reference angle divided by the hypotenuse. So that reduces to 1/2. Tangent is the opposite side of the green reference angle divided by the hypotenuse. Or excuse me, divided by the adjacent side. So we get negative root 3. Cosecant is the hypotenuse divided by the side opposite, and 8 over 4 reduces to 2 over 1. Multiply both sides by root 3 and we end up with the following ratio. Secant theta is the hypotenuse divided by the side adjacent the green reference angle, so we get 2. And cotangent theta is the side adjacent the green reference angle divided by the side opposite the green reference angle. So 4's cancel out, and we have negative 1 over root 3. Multiply both sides by root 3, and we have our final expression. So this was a special case where we have a recognizable triangle, and you can deal with this however you want, but notice that it doesn't really matter what x is. It's just going to reduce to a 30, 60, 90 triangle. Okay, so let's try the next one problem together. So negative 10, negative 10. Let's say that that's about here. That's a point on the terminal side of a reference angle in standard position. So that would be this angle here. And the reference angle is the green angle. And this side would be negative 10, and this side is negative 10. But notice that those two sides are equal in length. If this is a right triangle and those two sides are equal, then of course we're dealing with a 45, 45, 90 degree triangle. So that means that these angles are 45 degrees. So we don't have to use the Pythagorean theorem. That's really the only difference with these problems, is that we don't have to use the Pythagorean theorem. So if x, obviously x is 10, right? You see that? So the hypotenuse is 10 root 2. But we don't need x to be 10. We can choose any number for x. We could choose 1. 1 would be a lot easier. If you want to do that, you can. I'm just going to let x equal 10. And we'll bring this triangle down. So if x is 10, then the hypotenuse is 10 root 2. I'm going to draw that a little bigger. And the angle in question is this angle here. That's theta, and of course the green angle is the reference angle. So now we're ready to go. Sine theta is equal to the opposite side of the green reference angle divided by the hypotenuse. The 10s cancel out, and we're left with 1 over root 2, which is a very familiar ratio. We're going to multiply both sides by root 2, and we get negative root 2 over 2. Cosine theta is going to be the same thing. Remember, in a 45, 45, 90 triangle, cosine theta and sine theta are equal. Tangent theta is the side opposite the reference angle divided by the side adjacent, but you can see that's just equal to 1. See, these ratios are very familiar to us. Cosecant theta is the hypotenuse divided by the side opposite, and the 10s cancel out. We're left with negative root 2. Secant theta is the same thing as cosecant theta when you have a 45, 45, 90 triangle. Cotangent theta is the side adjacent, the green reference angle divided by the side opposite, which of course is 1. It's the same as tangent in a 45, 45, 90 triangle. So these problems are really the same problems that we did previously. The only difference is we didn't have to use a Pythagorean theorem because we could use special triangles to help us find the hypotenuse. So go ahead and try number 17. We'll just do 2 more problems today. With number 17, you're going to get a 30, 60, 90 degree triangle. So try 17. When you come back, we'll do it together. Okay, we're back. So 2 root 3 and 2. That would be maybe about there. So this side must be 2 root 3, and this side must be 2. And we see that this is a 30, 60, 90 degree triangle. This side is x. This side is x root 3, and this side is 2x, and you can see that x is equal to 2. So the hypotenuse of the triangle that we're looking for is going to be 4. So in the first quadrant, the reference angle is equal to the actual angle. And I think we have everything that we need. So we're ready to find those values. So sine theta is the opposite side of the red reference angle divided by the hypotenuse. And you see, because this is a 30, 60, 90 triangle, the ratio is very familiar. Cosine theta is the side adjacent to the red reference angle divided by the hypotenuse, and 2/4 reduces to 1/2. Very familiar ratio. Tangent theta is equal to the side opposite the red reference angle divided by the side adjacent. The 2's cancel out. Multiply both sides of the fraction by root 3, and we get root 3 over 3. Cosecant theta is the hypotenuse divided by the side opposite the red reference angle. So that would be 2. Secant theta is the hypotenuse divided by the side adjacent the red reference angle, which reduces to 2 over root 3. Multiply both sides by root 3, and we rationalize the denominator. Cotangent theta is the adjacent side of the red reference angle divided by the opposite side, and we get root 3. So there you go. If you got those answers, good. We didn't have to deal with negative numbers because the angle was in the, or it terminated in the first quadrant. Okay, we have one more problem today. Go ahead and try number 18. When you come back, we'll do it together. Okay, we're back. So we have a point in the second quadrant. It's about there. And that point is on the terminal side of an angle in standard position. We're going to call that angle theta. And the point is negative 5, 5. And this side is negative 5, obviously, and this side is 5 based on the definition of rectangular coordinates. And because those sides are the same, we know that this is a 45, 45, 90 triangle. So these angles are 45 degrees. And if those sides are the same length, then we know from our knowledge of 45, 45, 90 triangles that the hypotenuse must be x times root 2. But what is x? X is 5. So the hypotenuse is 5 root 2. So now we can draw a triangle down here that we can use to find the values we're looking for. Remember, the hypotenuse is always positive, and this angle here, theta, is the angle in question. And of course we have to consider the reference angle. Okay, so sine theta is the side opposite the green reference angle divided by the hypotenuse, and that reduces to 1 over root 2. Multiply both sides by root 2, and we get root 2 over 2. Cosine is going to be the same thing, except it's just going to be negative, because the adjacent side is negative 5. Tangent is a side opposite the green reference angle divided by the side adjacent, so we get negative 1. Cotangent is going to be the same thing as tangent, negative 1. Cosecant is the hypotenuse divided by the opposite side. The 5's cancel out. You're left with root 2. Secant is going to be the same thing except negative, because you're dividing by a negative 5 instead of a positive 5. So if you got those answers, good. So you're starting to get used to the 30, 60, 90 triangle, the 45, 45, 90 triangle, and how that applies to problems where you're given a point on the terminal side of an angle in standard position. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2. And number 3 and number 4 and number 5, number 6, and number 7, number 8, number 9, number 10, and 11. Now don't go before you get your homework. Here's screenshot number 1 of your homework. Be sure to do this homework completely and correctly and neatly and put it in order in your binder. Here's screenshot number 2. Remember, if you don't do the homework, it's 100% guarantee you're going to learn absolutely nothing in this entire course. And screenshot number 3 of the homework. And number 4, but don't go before you get the answers. Remember, it's not enough just to attempt the homework, you must do it correctly, so you must check your answers. So here's screenshot number 1 of the answers, and screenshot number 2. So get that homework done, and I'll look forward to seeing you in the next class.